I'm very happy to present Luka Jacobowitz. I hope I pronounce it correct.
Yeah, more or less.
Yeah, you probably all know Luka. He's a great contributor into lots of cats-related open source project. He's also maintainer of this OutWatch project. What was the name?
Yeah.
Yes, I think it's OutWatch.
OutWatch.
Like a reactive UI application.
I haven't touched that in a long time, but yeah.
So, and probably he will tell us something about monoids today, I guess. So it is not a teaser anymore. He spoiled the entire topic. So please, Luka, you're welcome. Let's give a round of applause to Luka. Virtual applause, sure.
Virtual applause. Hey, thank you so much. Yeah, my name is Luka. This talk is titled Monoids, 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 and it is surprisingly about monoids and a fun ride through abstract algebra and type theory. So a little bit about me. I work at ComStack, which is a smaller startup here in New York City, doing real estate, building a real estate platform, commercial real estate platform using pure functional Scala, and I really, really enjoy it. The other part is that I maintain a lot of various type level libraries, mostly cats and their partner projects like Cats Effect, Cats Collections, Cats Tagless. And I'm really, really enthusiastic about functional programming and the more theoretical side of Scala. And yeah, so without further ado, let's get started. I am going to talk today about monoids, obviously. And then after that, we will be talking about monoids, some more monoids, and lastly, but not leastly, monoids. No, okay. I did this joke before, and usually when you can hear the audience laugh, you know that it kind of landed, but now it's like, I don't know. But yeah, for real though, I'm going to talk about monoids, but I'm also going to talk about like abstract algebra and how monoids and abstract algebra relate, and also type theory and how that plays into the past 2 points. All right, so a quick introduction about monoids. For those that don't know about monoids, in cats, we have this type class called monoid, and it's basically defined by these 2 functions, empty and combine. And empty basically just tells you, hey, for subtype A, I can give you this sort of empty value of A. And combine just basically takes 2 of these A's and combines them into 1. So the very simple example for this is integer addition. And so we can create this monoid for integer, and this is actually a definition from the cats library, where empty is 0 and combine is just adding the 2 numbers, the 2 integers together. And you can see how that kind of makes sense. So going further than this, why is this useful? We can use this for a lot of different things. So for example, if we have a list of integers, we can combine all of them by using fold left, using 0 as a seed, and then using addition for combining all the integers inside. But you can do the same thing with strings, with the empty string as a seed, and string concatenation. But we could also do something like combining all the sets by forming the union of all of those sets by using the empty set as the seed. And we could also do this for pretty much anything that defines a monoid. And this is really where the power and the usefulness of monoid comes into play, because all of these 3 functions here can be generalized to this combine all function that is a part of cats. And basically it says here T colon monoid, which basically says that T has to have a monoid instance in scope. And then we can go from a list of T to a single T simply by combining all of them using the empty method of that monoid as the seed. So that's pretty neat. So moving along, we can find monoids pretty much everywhere. Like I think there's probably upwards of 50 monoid definitions in cats. Don't quote me on that though, I'm not sure. That's just an estimate. And this is also why the talk's titled monoids, 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 because they are everywhere. So for example, in cats, we have this definition where if we have a function from A to B and that B has a monoid instance, then the function from A to B also becomes a monoid. And we can also combine these functions now. Same goes for an option of A, where A has a monoid instance. So then that option of A becomes a monoid. The same goes for tuple. If we have a monoid on both sides, now we have a monoid for that tuple. We can do the same thing for the map monoid, for Scala's map, where if the values, the B type here, the value type of the map has a monoid, then we can start combining maps using that monoid. Same goes for something like IO. If we want to combine two IOs, we can do that if that A inside of that IO has a monoid. So these are just a select few examples, but there is tons and tons more. And the real useful part comes in their composability. So for example, we have this neat little example that I like to use where basically we have this this function right here where basically we have this data variable right here. Can you see my mouse? Probably. This data variable is just some form of text, and we use fold map, which is basically like combine all combined with map. So we basically take, so this is a list of strings, some kind of text, and we run this step function on each of those strings. And since it's a text, these are going to be words. And what we do is return a tuple of 1, the length of the word, and a map from word to 1. And because of the monoid instances in this case, this gives us the number of words in this text, the number of characters in this text, and the occurrences of each word in this text. So this here is a map from string to int, right? And so this will also be a map of string to int, where the string is the word and the int is the number of times that word appeared in this text. So this is neat, but we can reuse the same function for something like a stream, where we could use something like scanmap to give us like an intermediary view of some kind of stream using these same metrics. And this is all supported outside of the box using FS2 or Monix. And of course, if you just use cats, you can use this on any kind of collection like list or vector or sets or anything like that. So this is really cool, and it makes it like a real general thing you could use a lot. And certainly I use it all the time in production code. So one thing about monoids that is very important and makes this whole thing kind of work are monoid laws. And the first law is the law of associativity. And this is like pretty much the most important law. And it basically says that we can move these parentheses around without changing the result, right? So if you do first x plus y, or I'm just going to pronounce this plus, even though it's like x combined with y, but that's too long. X plus y plus z or z has to be the same as x plus y plus z. And this may seem obvious, or like this may seem like something every monoid should do. Like it's just like some intuitive thing because like most numbers work that way. And yeah, but it's really important, and we will see in a minute why. And then we also have this law called right identity, where if we combine something with empty, it has to stay the same. So basically it doesn't modify it at all. And the same goes if you put it on the left. So empty plus x is also x. And that's basically the definition of a monoid. So you have these two functions, or these two operations, and these three laws. And That's pretty much it. So why would you need this? Basically, if you think about a number of elements in some sort of list, some sort of stream, anything, right? I called it here A, B, C, D, E, F, G, and you want to like capture them all together, like combine them all together. You could do that simply by saying, hey, I just want to have this as a list and then call combine all, or maybe it's a stream, maybe it doesn't fit in memory, right? Because it's too large. And but still, you would just simply go through it sequentially, start from A and go to G. But with associativity, what this gives us is these kinds of transformations, right? So these two definitions right here are identical simply because of associativity, right? Associativity means we can move around these parentheses. So now these things are exactly equivalent, as long as the monoid in question holds the monoid laws, abides by the monoid laws. And that means essentially we can parallelize any associative operation. So instead of taking, like, let's say 1,000,000 elements, or let's say 1 billion elements, and doing it all sequentially, we can take chunks out of them and then basically combine all these chunks in parallel, and at the end combine all of their results. And because of the monoid law, because of associativity, these have to be the same thing definitionally. Right. And so if you have a stream of some A which has a monoid, and you want to do this in parallel, you define this max parallel thing. Basically, this is the whole code you need to get this done. So you basically chunk them in some kind of way, which gives you these smaller chunks. And then you use this map async function. And basically, right here, this is a chunk. So you use combine all on the chunk, return that in IO. And then this basically gives you a stream of A again. And then you compile and use this fold monoid, which basically takes a stream of A and returns an IO of A, where all of the A's were combined using the monoid of A. So yeah, this just works, and it's really nice. So monoid is a type of algebraic structure, and these monoid laws are algebraic laws. That's just how mathematicians call them. Don't ask me, I'm not one of them. But so yeah, there's many laws, not just associativity and identity, which is the ones we looked at, but there's also something like invertibility, commutativity, which probably most of you have heard of. I learned it at school, like 6th grade or something. Something called idempotency or idempotency, or I don't even know how to pronounce this thing, but it is what it is. And we also have absorption and distributivity. So these are a bunch of different laws, and pretty much all of them are present to some degree in cats. And we'll kind of have a look at what this is. And this is part of this is basically what abstract algebra is all about, defining these algebraic structures in order using these kinds of laws. So if we look at Cat's kernel, this is one of Rob Norris's type class diagram. This is where monoid and semigroup come from, and it looks like some kind of thing. And I remember first looking at this and being like, "Ooh, okay, where do I even start?" At least like monoid and semigroup, because they're more important, they're like highlighted, which is good. But what the hell is a band or a bounded semilattice, and what are all these arrows? It looks a bit confusing, but I hope after this talk it will make sense. And so basically, all of these structures are just like monoids, but they have different laws. That's basically the only difference. So we have this diagram right here, and basically, if you want to know what a structure is, you can basically just look, oh, okay, a commutative monoid right here is just a monoid that has to be commutative, and that's probably fairly obvious from the name. But something like a semigroup is just a monoid without the identity. So semigroup is just like monoid, but it doesn't have this empty function, which means it doesn't have an identity. And yeah, so what we're going to do is we're going to look at some of these structures to kind of see what they are and how these laws look and what kind of instances we could find in Scala or in programming in general. So first thing is this thing called groups. And groups in Scala terms extend monoids. So every group is also a monoid. And the basic thing is that in addition to all of the monoid laws and the monoid operations, we have this inverse function, which takes into A and basically inverts it and returns another A. So the one law that is defined extra here is the inverse law or invertibility law, where if you combine something with its inverse, that now becomes the identity or empty. And of course, this goes both ways. It doesn't matter if it's on the left or the right-hand side. And so there's something obviously where with addition and where the inverse is just basically multiplying by -1. So 5 plus -5, right? So -5 is the inverse of 5. When you combine those by addition, you get 0, which is the identity. So integer addition forms a group. And so does integer multiplication, or I guess not integer multiplication because you can't have, but some kind of number that supports whatever these things are called in English. Brüche in German. My mind is blanking, I'm sorry. But yeah, so if you multiply 4 by its inverse, by its multiplicative inverse, which is 1/4, you get 1, which is the multiplicative identity, right? So if you multiply something by 1, you always get back that same number. So those are two groups defined on numbers, but we can also define it for something like a set, where the symmetric difference of a set is a group, right? And the interesting thing is that this is a special kind of group where the inverse is actually itself, right? So the inverse of set 1, 2, 3 is also set 1, 2, 3. But if you then use the symmetric difference on the two, you still get the set. And it's still a very valid group, even though the definition is kind of weird, right? So you wouldn't expect the inverse of something to be the same thing. But this is something you can you kind of come along with like an abstract algebra. This is so abstract that sometimes the intuition of something like inverse is a bit misleading. Same with like something like combine. Sometimes combining doesn't actually mean combining. It means it's just the abstract notion of combining or inversing. And the only thing that is needed for this kind of, for something to be a group or to be a monoid is that it abides by these laws. And when it does, it does. And when it does, it is. All right. So those are groups. What else can we do with groups? So one really interesting thing is that Rubik's cubes all actually rely a lot, or like solving Rubik's cubes relies on a lot of like group theory, and it's really interesting. And my friend Stuart Stewart actually gave a really nice talk on Rubik's cubes and how you can do stuff with them in Scala using groups. And I really recommend checking it out if you're interested in that kind of stuff. I'm not great at solving Rubik's cubes, but I've solved a 5x5 like 20 times, and then I got bored of it, but it's cool. All right. Another really cool thing we can do with groups is have these kinds of negative lists, where basically instead of having just elements, you could also have like negative elements. And so basically that gives you a way to say, oh, okay, it gives you some kind of like historization to a degree, but you can also say, okay, I don't want this to appear in my list, so I'm just going to concatenate a remove node with this. And I wish I had more time to talk about this experiment that I did, but I'm kind of short on time, so I'm just gonna keep going. Next. are semilattices, which is another really interesting algebraic structure. And semilattices are basically semigroups, so they don't have an identity, but they are commutative and they're also idempotent. And commutativity basically says that if you combine A with B, that has to be the same as B combined with A. And idempotency says that if you combine anything with itself, it remains the same. And so this kind of limits a lot of things. But other than that, it's basically exactly like a semigroup. So it has to be associative, has to be commutative, and idempotent. And we have a lot of different things we can look at here. So for example, my first example here is if you use Boolean algebra and you say true and false, that is the same as false and true. So and, Boolean and is commutative, and it's also idempotent, right? True and true is still true. False and false is still false. And the same goes for Boolean or, right? True or true is still true. And false or false would also be still false. And the other thing is, of course, set operations, right? So if you have a set of 1, 2, 3 and you union that with itself, that's still going to remain the same. Same for the intersection. And another thing is taking the max of any kind of ordered element. So for example, the max of 7 and 7 is still 7. Same with the minimum of 7 and 7. It would also be still 7. And so max and min are so-called semilattices. And this is kind of what I mean by it's kind of like counterintuitive. Like if you take the max of two things, you don't really usually see it as combining them in a way. But as I said before, the only thing that matters is the laws in this mathematical sense. So they are still semilattices and by extension semigroups. Okay, what can we do with semilattices? What else is there? So idempotency is a really important thing if you look at like distributed systems or something like Amazon SQS. When you have like some kind of at least once delivery, because you can't guarantee that a message will be delivered exactly once. And this is where idempotency really comes in handy, because if you want to send something, you have to make sure that if it comes twice, that doesn't like completely throw you off guard. And if you prove that your algebra that you use for this kind of thing is idempotent, that means you're basically safe on that regard. Another thing is like, I've talked about set intersections and set unions, but the same goes for like geometry operations, where if you take like a polygon and another polygon and you form their intersection, that is also, of course, idempotent and commutative, or the union of that. And that's something I've come across in my job recently. Or something like, as I said before, using updating state in a distributed system where you don't have this kind of guarantee that everything will always be delivered to all these different nodes. So something like CRDTs can be modeled very well using semilattices. And in fact, I think it's been done in the CATS book by, I want to say, Noel Welch and Dave Gronell. Yeah, and basically any situation you might need idempotency, you can model it mostly as a semilattice or something similar. So yeah, that basically gives us this chart, which we should now be able to read more or less. So we've seen semigroup, we've seen commutative semigroup, monoid. Band is exactly like a semilattice, but it does not have commutativity, right? So band is just associative and idempotent, but doesn't have to be commutative. Yeah, and then we have group and commutative group and commutative monoid, which are just commutative forms of their structures. And then bounded semilattice is like a semilattice, but adds an identity. So yeah, that's the basic algebraic structures we learned. And now we're going to look at the two laws that I mentioned earlier that we haven't spoken about earlier, and those are absorption and distributivity. And for that, we have to look at ring-like structures. And ring-like structures are a bit more involved. So we're going to look first at a semi-ring. And a semi-ring can be seen kind of as something where we can take both, you both have like an additive method, plus, but also a multiplicative method, times. And then you also have this zero right here that is basically like an empty for plus, right? So 0 is the identity for plus. And basically that's exactly what it is. Like plus and 0 have to form a monoid, and times has to be associative. So it has to be a semigroup. So in other words, plus forms a commutative monoid with 0 as an identity, and times forms a semigroup. And that is the whole definition of a semi-ring, or semi-ring, whatever you want to call it. Yeah, and this is a semi-ring, but there's tons of other ring-like structures. Actually, let's first go into absorption. Sorry about that. So the important part of this absorption law is that this 0 interacts with the times function. So if we multiply by 0, we know, like in numbers terms, that always becomes 0. And semi-ring is kind of like the abstraction of that. So if you multiply, or if you use this times method with this 0, then it becomes 0. So it absorbs anything you put into it, kind of. That's the intuition. And then we also have the distributivity, where plus has to distribute, times has to distribute over plus. And basically what this means is if we do a times b plus c, that has to be the same as a times b plus a times c. And this is something that probably most of you know happens with numbers, but there is lots of other things that also have the same kind of behavior. So we have a semi-ring, which is a commutative additive monoid and a multiplicative semigroup. So what if we kind of had a group in the additive part, right? So if we had a commutative additive group and a multiplicative semigroup, we get what's called a rung, mathematicians. And if we have two monoids, one a commutative additive monoid and a multiplicative monoid, we have a rig. And if we have both a commutative additive group and a multiplicative monoid, we get a ring. And you can kind of see where these names come from, rung and rig, by basically saying rig is a ring without n, without negation, right? Because it's only a group on the additive, so you can't negate it. And rung is a ring without the I, without the identity, because it's just a semigroup that doesn't have an identity. So that's like something you can remember if you want. And then if both are field groups, right, if we can call the inverse on both of these, we get what's called a field. So those are ring-like structures. And then we have to also look at lattices, which are similar in a way that they both have also two operations that kind of operate, but instead of forming on multiplicative and additive, they look a little bit differently. So basically, if we have two semi-lattices on the same type, we get a lattice. And if we have two bounded semi-lattices, we get a bounded lattice. And two semi-lattices that distribute over another, right, that is called a distributive lattice. Two bounded semi-lattices that distribute over another is called a bounded distributive lattice. It's quite a mouthful, but it is what it is. Yeah, sorry about that. So the next thing I want to talk about, this was the abstract algebra part. And the next thing I want to kind of talk about is the type 3 part, because Scala's type system is really, really interesting, and it's only going to get more interesting with the upcoming Scala 3. And so I want to look at something that is here in the title called monoids at the type level. And I'll show you in a second what that means. So we've talked about these algebraic structures at the value level, right? So if we combine two values of A to form a new A, but we can also do that same thing at the type level, right? So instead of combining two values of type A, we combine two different types. So we combine type A and B. And so, for example, one of these things are product types, right? So we can combine a type A and a type B by using a product type, which in Scala is a tuple, for example, right? So I'm going to claim that these product types are monoids at the type level because they are associative, right? So A tupled with B and C is equivalent or isomorphic to a tuple of A, B, and C, right? You can see that these things are exactly the same. And by isomorphic, I basically just mean that you can go from one side to the other side without losing any information. So you can go there and back, and it will still be the same thing. So they are associative, and they also follow the identity law, right? So if you tuple something with unit, that doesn't give it any extra information, right? So A tupled with unit, you can turn that into A, and you can go back to A with unit a million times, and the thing will always be the same because unit doesn't have any information. Yeah, and that is also unit tupled with A. It's also the same. So product types are monoids. What about sum types? So yeah, sorry. Product types are also basically, that's why they're called product types, is because they're akin to the Cartesian product of the set of inhabitants of the two types. So if we look at this in like this sort of Venn-ish diagram, it's not a real Venn diagram, we can see that the tuple of x, y, its inhabitants, right? So if x is a type that is either A, B, or C, and y is a type that is 1 or 2, the tuple of x and y, which is a new type in itself, now has the Cartesian product as its inhabitants. And if we do this with unit, we can kind of see here, oh, these things are pretty much the same, right? There's just like some extra parentheses and a comma. All right, so we can do the same thing with sum types. Getting ahead of myself, sorry. Where the associativity law still holds, right? So either A, either B, or C is the same as either A and B or C. And basically, both of these types just mean there's at least one of an A or a B or a C in this type somewhere. And you can go from one to the other and back again easily. And the identity is formed with this special type called nothing. And nothing is a type that has no inhabitants, right? So there can never be a value for nothing unless you throw an exception or recurse indefinitely, but we're kind of like gonna discount that and not talk about it. So either A or nothing is always going to be a left because it can't be a right, because then it would have a value of nothing, which it can't have. So basically it's always a left, and that means it's always an A. And this is akin to the disjoint union of the set of inhabitants, right? So if we look at a set of inhabitants using our same x applies earlier, we can kind of see that either x and y, its inhabitants, are kind of like the disjoint union of those two sets, x and y. And here we have A, B, C, 1, 2. And the cool thing about this is that if we looked at the product type, tuple x, y, we had 6 distinct inhabitants because there was kind of like 3 times 2. And here we have 5 because it's kind of like 3 plus 2, right? So it's a sum, whereas with tuple, it was a product, right? We multiplied. So yeah, there's lots of these different analogies that kind of start to make sense if you think about the theory and how these kind of things work. And if you do the same thing here with nothing, which is 0, you basically add 0 which is always going to be the same, right? So 3 plus 0 is still 3. Yeah, and so these things, again, these two sets are isomorphic. They're pretty much identical. All right, so some types are monoids, product types are monoids. How is this relevant? Actually, I'm glad you asked, even though you didn't. We have this thing called semigroupal in cats, and it is basically at the foundation of pretty much all libraries that depend on cats that I know of. And it defines this product function that takes an f of A and an f of B and turns that into an f of tuple AB. So basically, what we said earlier is if we combine two types and form a tuple type, this is basically like that applied to a higher kinded functor, a higher kinded semigroup, sorry. So we have an f of A and an f of B, and we merge those two f's together into one f, and now what we get is, instead of A or B, we get the tuple of A and B. And this is then extended, which makes apply basically in mathematicians' terms, it makes it a semi-groupal functor, whereas applicative is a monoidal functor, which I'm going to get into. And yeah, if you have product and map, which you can get from functor right here, that basically gives you apply. So apply is nothing else but product plus map. And it is defined by this app function, which is basically just a different method to get to the same thing, right? So you can get product by using app, but you can also get app by using product and map. All right, so apply is a semigroupal functor, and if we then kind of like went further and added a unit function to this, right, which returned an f of unit, you would get a monoidal. And actually, this is pretty much exactly what applicative is, right? So we use the identity of our product type monoid, right, of the tuple monoid, so to say, the higher, the type level tuple monoid, and added the unit identity, and that gave us a monoidal functor, which is called applicative. And applicative is defined in terms of pure, but pure and this unit function are identical, or they can be defined in terms of each other if you have map again, which we do because it's a functor. So yeah, and the cool thing is we can do the same with sum types again. So we have this sum semigroupal that takes an f of A and an f of B and returns, instead of an f of tuple AB, an f of either AB. And then we could make this a monoidal by adding this nothing method, which just returns an f of nothing. And actually, this kind of exists in cats already, and you might have come across it. So yeah, instead of sum, we have combined k, but we can see here, if we have a functor again, we have this map function, these are the same, right? Merge is a function that takes an either of A and returns an A, right? Because it just, if it's the left side, it returns that A, and if it's the right side, it returns that A. So if we had a functor here, map, these two functions would be exactly identical. And then with monoid K, which is similar to our sum monoidal we saw a slide earlier, instead of having this nothing function, you have this empty function, which is just for all A, f of A. And basically in Scala, this means that because this is a universal constraint, this could be anything, and this could also be nothing. So these are also identical. Yeah, so we basically have sum and product types, which are monoids at the type level, and then we also have them encoded as functors, as like higher kinded algebraic structures, higher kinded semigroups, and higher kinded monoids. So it's pretty cool. And we can see these like differences by looking at the iteration functions that are defined in cats. So for example, fold map is the simplest, and it just takes an f of A, which is some kind of foldable, like a list or an option or whatever, a vector, and it takes a function from A to M, where M is a monoid, and then it combines all of them and returns a single M. You can do the same thing with full map K, where we have some kind of G, which is monoid K, and instead of going from A to M, we go to A to G of B, and then at the end we return a G of B. And actually, one of my favorite functions, traverse, is kind of the same thing. We have an applicative instead of a monoid or a monoid K, and we go, again, from A to G of B. But instead of tearing it all down, we kind of get back this F inside here. So instead of getting just a G of B, we get a G of F of B. And full map M, which is basically the same thing with the monad, is also basically the same idea, right? And so what I'm claiming here is what I said earlier before the talk, is that monads are kind of just like monoids, and you can see that if you look at the laws. So the laws are always kind of the same. We have the monoid laws here with associativity and identity. And the applicative laws kind of look the same way. I made them look a bit easier for the purposes of this talk. But basically, that's what they are. They have associativity and identity laws. And the same for monoid K, right? So if it's associativity and identity. And the same does indeed apply to monads. It just looks a little different because the types in play are different. But a monad is just a different flavor of monoid, where you have this function. So if you do FA, flat map A to F of A, flat map G, and if you move the parentheses around and first do this FA to F flat map like this, those have to be the same, and that's just associativity. We're just moving around parentheses. And if we use pure, again, which we also did here in applicative, which is the identity, and then we just flat map to FA, which is basically what is the same as here, empty plus X, or empty plus FA, that is just FA. And those are the only thing that defines a monad. So monads are essentially just monoids, just with a kind of different flavor. And if you go into category theory, they have, you can get into all kinds of different like formulations of how these two things relate. But this talk is not about category theory, so I'm going to not do that. All right, so the cool thing about this is that summon product types, not only are they monoids, but they're commutative monoids, and together they form a commutative ring. And so what that means, basically, is they also absorb and distribute. So the absorption law basically says that if I multiply something by 0, it also becomes 0. And so if we look at this type chart right here, where multiplication is a product type, tuple, and 0 is the identity for the sum type, either, nothing. If we take a tuple of A and nothing, which is what this is, that becomes nothing, because we can't put a value into that tuple, right? So tuple of A and nothing is the same as nothing. And the distributivity law basically claims that A times B plus C is A times B plus A times C. And I'm not going to show you a proof for this, but you can definitely easily do this. Like if you have a tuple of A, either B, C, you can turn that into an either A tuple B or A tuple C. You can do it for yourself. It's actually like a fun type Tetris exercise. So, and of course, commutativity is that if you have an either A and B, you can also always turn that into an either B and A without losing information. And the same goes for tuple, right? You can swap them without anything bad happening. All right. So yeah, we have a commutative rig, and we can kind of show this where if we here form the intersection, right? No, not the intersection, sorry. The Cartesian product between X and nothing, which is the tuple of X and nothing, we don't get any values here, right? So that holds that absorption law holds. And just like with applicative and monoid K, we can do the same thing here for this kind of structure, which is alternative, which uses both these sum and product functions and pure and empty. And this is also found in cats and yeah, actually used a lot for a lot of different methods. So this is really interesting to me. We have all of these like abstract things, but they all turn out to be this this type class that is used every day by lots and lots of programmers. And they don't even know about, oh, okay, what alternative is a high candidate rig? What the hell does that mean? I hope like this kind of gives some insight to that. And now we're going to talk about union types, which is a new feature in Scala 3. And where we saw sum and product types go into like the ring hierarchy, union and intersection types are going to go into the lattice hierarchy. So union types are bounded semilattices. What does that mean? They are associative. A or B or C is the same as A or B or C with the parentheses. And the cool thing about this is not only are they isomorphic, but they're actually identical, right? I use this different symbol right here, equals colon equals. And basically, the difference here is that we don't have to say, oh, we can turn this into the other thing and back again. What we can do is just have the compiler prove it for us, right? So if we have a value of this type and we have a function that takes a value of this type, we can always put in a value of this type because the compiler actually treats them as equals, and that's really cool. So associativity law, identity law, if you A or nothing, that still gives you A. Commutativity law, these are actually commutative. Idempotency, right? So if you have A or A, that is just A. And again, the compiler will treat all of these as the same. And this is akin to the union of the set of inhabitants of those two types. And this is kind of distinct from the disjoint union that was either. And that is because of this right here, the idempotency law. If you had either A or A, you could still like discriminate, oh, is this on the left side or is this on the right side? Whereas here, you can't because these are treated as the same as just A. And yeah, I talked about this, got ahead of myself again. We have these different equivalence relationships where equals colon equals means the compiler can actually treat them as equal, and here it's just this isomorphism. And yeah, these are the differences between sum and union types in this Venn-ish diagram, where if we form the union type right here, this is just A, B, and C, and it's just, we only have 3 inhabitants, whereas here we actually have 5 because it matters if it's on the left, and we can actually look if it's on the left, whereas here we can't, we don't see if it's on the left or not. Yeah. And this is the difference between, again, the union and the disjoint union in set theory. Yeah, so union types are bounded semilattices, which means that if we take the union of X and nothing, that will just give us X. And here we have no nasty parentheses. These are actually the same. We can kind of see that here. And intersection types are very similar. Right, we have associativity, we have identity, except here we don't use unit or nothing, we use any. And we have commutativity, which is actually new in Scala 3. We used to have with, A with B, but that was not always equal to B with A. And this is a new guarantee in Scala 3, and it's really nice. And of course, idempotency. And this is, well, just as the name says, akin to the intersection of their respective set of inhabitants. So if we look at this Venn diagram, ABC is X, Y is ABD, the intersection is going to be AB. And if we use any, which is just which has all values or all types and its inhabitants here, that if you intersect with any, you're always going to get the same thing. So X and any is the same as X. And together they form a bounded distributive lattice. So we have idempotency, we have absorption, which basically says that if you union with any, you get back any. If you intersect with nothing, you get back nothing. And you also have distributivity. And the cool thing here is that I don't have to, like, the distributivity of sum and product types, I was like, oh yeah, you do it yourself. But in this case, we can actually just let the compiler do it, because the compiler will actually see these two types, or these two types, or these two types is equal. Yeah, we can see this again in these Venn diagrams. If we union with any, that is going to, any is going to absorb this X. So X or any, X union any is the same as any. And the same goes for intersection with nothing, where if we intersect with nothing, you know, those two sets right here, they don't have an intersection. So this just becomes nothing. So how is this useful? I don't know yet. So, but one thing to think about is that Scholar 3 is coming up, and that means we get these new types, this new type system, and we can play around with it in libraries like CATS, and we can experiment with it. So for example, we could have this kind of union monoidal, which could be a new type class in a Scholar 3 version of CATS, where if we have an f of a and an f of b, instead of returning a tuple or an either, we could have something like a union of a or b. And with something like empty, again, which is akin to nothing. And then combine k, which is really cool to me, is just the union of x and y, right? Because if you think about it, we have an f of a and an f of a. If we use union on these two, we would get an f of a union a. But as we know, a union a is equivalent, or is exactly equal to a. And so combine k would just be a specialization of this union function. And we could also do something like sum if we just map and wrap them into left or right at the beginning, so to kind of like discriminate. And this is why also like either is sometimes called, or a discriminated union or a disjoint union, because we can kind of say, oh, okay, I want all the A's on the left side, I want all the B's on the right side. Yeah, so we can kind of, like, a union monoidal could be maybe a supertype of semigroup K. Who knows? We'll have to play around with this. But to me, this is really interesting, because this is kind of like a lot of the abstractions we have right now are abstractions we got from languages like Haskell. And Haskell doesn't have this, so that they never had a chance to even come up with these abstractions. And now we do have this chance, and who knows what we can come up with. Yeah. And some other cool things or useful things that are like isomorphic or equivalent is that either unit in A is the same as option of A, right? Either nothing or A is the same as A. A or unit is the same as A. We already see this, but we can also see this in the type classes that they have. Someone giving me a chat, the Q&A room. Okay. Where applicative error, which is something that is used for error handling, when unit is the error type, that is actually the same as alternative, simply because of this difference right here, right? Option is kind of like the standard instance for alternative, and applicative error is kind of like the same with either, but because either unit in A is option of A, or is isomorphic to option of A, these things are also equivalent. And the same goes for monad error, where we use nothing. That's just the same as monad, because we can't raise any errors because they're nothing. And the same goes for monad writer, which is kind of like a tuple. And if we use unit there, this thing basically means that these are also equal. So I also have another cool snippet called glist, where something we could do is like a generalized list, where the head could be either A or B, and then something like nil would extend glist with nothing or B, which basically would mean that the head is always B. And so in this case, a list would just be a glist of A in unit. So the head would also always be A or unit, which is basically mean. Oh, sorry. Where was I with this? Oh yeah, and then we can define the non-empty list as A or nothing, which is just A. So basically what this means is that we could have the same structure for list or non-empty list. And if we call head, we either get A or unit, or in this case, A or nothing. So we can kind of use these things to generalize a lot of different things. So other cool stuff I want to mention here, because I'm kind of running out of time, is
we are running, really much out of time. So
yeah. All right. I'm just gonna round this up. I think we're pretty much done. So monoid arrow is actually two monoids based on either. Parallel is also two monoids. So all of these like different kind of type classes, they're all always somehow related to monoids, which is what this whole thing is about. Categories and category theory also based on monoids. Cat's retry policy is surprisingly a bounded distributive lattice. And free and co-free also have this kind of duality between product and sum types, where free is based on product types and co-free on sum types. Animations are also based on, can also be modeled like as a semi-ring. So yeah, in conclusion, we have all these different algebraic structures, and they all play really nicely together because they have like a common definition. And we can use these higher kind of type classes, and that makes them really useful. Like applicative is used pretty much every day by a lot of programmers, and it's just an extension of that. And we learned a lot about the properties of Scala's type system and how Scala 3 comes into play, and how these relate to these algebraic structures we talked about. And yeah, that's pretty much it. Thank you so much. We're hiring at Comstack right now. So if you want to know about that, listen, talk to me. And thank you so much for listening. You can find my Twitter at Luka Jacobowitz or on GitHub, but I'm also going to be around anywhere. You can always hit me up. All right, I guess I should go to the Q&A room.
Yes, Luka, thanks a lot. So let's give a round of applause to Luka. We don't have time for questions and answers, but
okay,
you can ask Luka everything in the Q&A room. So please follow it. And I'm very, very sorry. We need to prepare the next presenter.
Yeah, sorry about going on.
Oh, no worries there. That was an amazing talk. Thank you so much.
Thank you so much. Thanks for inviting me.